Greetings, I'm Prathamesh Patham, present along with Rahi, Kunj and Amish presenting our project where we developed a real-time image classification system using convolution neural networks. The idea behind our project is to train a machine learning model that can recognize and classify image into one of the 10 categories. This technology has real-world application in areas like autonomous vehicle, medical imaging and security systems. The expected output of our project is simple but powerful. The user uploads an image, the model processes it, and predicts the most likely category. Finally, it displays the original image and the predicted label on the screen. For this, we've used the CIFAR 10 dataset, a well known benchmark dataset containing 60,000 color images from 10 distinct classes such as airplane, cat, dog, and truck, etc. The libraries we've used are TensorFlow and Keras for building the model, NumPy for data handling, Matplotlib for visualization, and PIL for image processing.
Hey guys, Avnish here. I would be explaining you further with the libraries used, the objectives of our project, the dataset, and the CNN architecture. So I would like to talk about the libraries used, which are the TensorFlows, the Keras, the NumPy, Matplotlib, PIL, and Google Colab files. So here we have imported them, and previously we have installed the TensorFlows as well. Now talking about the project objective to develop a CNN model which classifies the images into 10 categories. So we have made the objectives such as that the users can upload their own images and the CNN would be capable enough to tell the result. So now to train the CNN, we have used the CIFAR 10 dataset, which is very widely used in this domain, and here it is. So it consists of 60,032 into 32 color images in 10 classes, which are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. So the dataset is split into 50,000 training images and 10,000 testing images, and each image is 32 by 32 pixels. So now we would be going on to our neural network. So in that you can see this line. It is our first layer. It uses 32 filters of size 3 by 3 to scan the image and extract features. We use the ReLU activation to add non-linearity and set the input size as 32 by 32 with 3 color channels. Now going on ahead, this is the second convolutional block which increases the number of filters to 64, which helps the model learn more complex patterns followed again by the pooling. Now coming to this line, this is the third convolutional layer which improves the model ability to recognize detailed pattern and textures in the images. And this flattens the 3D output from the previous layer into 1D vector for the dense connected layer. Finally, the output layer contains 10 neurons, one for each image class. These outputs will later be converted into probabilities using a softmax layer. The CNN architecture is compact, efficient, and gives solid performance on a dataset like CIFAR 10.
Hello, this is Kunj Gohil. Let us see model compilation function. First, we compile the model. This step defines how the model learns. We use the ADAM optimizer, which is an adaptive learning rate optimizer that's well suited for deep learning tasks. We also track accuracy as a metric to measure how often the model's predictions match the actual labels. Now, let us take a look at model training. The fit function starts the training process. We train the model for 10 epochs, which means the entire training dataset is passed through the model 10 times. Along with training data, we provide validation data using the test set. This helps monitor how well the model generalizes to unseen data after every epoch. Over this 10 epochs, the model continuously adjusts its internal parameters to reduce the error. That's what training is all about. Now let us have a look at model evaluation. Once training is complete, we evaluate the model using the test set. This step gives us two metrics, test loss and test ACK. Test loss means how well the model is minimizing errors on unseen data, and test ACK means the accuracy of predictions on the test datasets. With our CNN and 10 epochs of training, we achieved around 65 to 70% test accuracy, which is quite good for a basic model trained for CIFAR 10. This results show that the model has successfully learned to classify images across all 10 categories, not just memorizing training data but actually generalizing to new inputs. In the next step, we use this training model to classify custom images uploaded by the users, and that's what Rahi will now explain.
This is Rahi. Now that a model is trained and evaluated, the final step was to make the system interactive, allowing users to upload their own images and get real-time predictions. Image upload and pre-processing. First, we prompt the user to upload an image using Collab's file upload system. The uploaded image is converted to a RGB to ensure compatibility. Then we resize it to 32 into 32 pixels, the same size as CIFAR 10 images. It's converted into NumPy array, normalized and reshaped to fit the model's input format. Prediction. We pass the image into our trained model. The model outputs probabilities for each of the 10 classes. Using np.argmax function, we select the class with the highest probability and map it to a human readable label using the class name list. Display results. Finally, we display the original uploaded image with the predicted class label shown as the title. This makes the experience clear, interactive, and user-friendly. Now I will give a demonstration of how our code works. So this is how our code works. Conclusion. To sum up, this project demonstrates how we can use convolution neural networks to automate the task of image classification. We trained the model on a standardized dataset, tested it for accuracy, and even enabled real-time prediction from user input. While we built a basic version, this concept has vast applications from medical image diagnostics to object recognition in autonomous vehicles. This project helped us understand not just how AI models are trained, but also how they can be integrated into real world applications. Thank you.